Good morning again. Today we're going to study DC machines. This is a continuation of what we saw in the previous lectures. Today we're going to study, though, a principle that is a little bit different. The principle of operation is slightly different than stepper motors. We're going to see how DC machines operate. We briefly addressed DC machines, that is to say, an electrical motor, in control systems, and today we're going to dig a bit deeper and see where, for example, those torque and speed constants came from, and how we can model the interaction between the magnetic field in the stator and the rotor, and how that creates continuous rotation. So we're going to address DC machines. That means a generator and a DC motor. They work on both ways. So by the end of this lecture, you should be able to understand how a DC machine operates, either as a motor or a generator, analyze and understand the different architectures of DC machines, and model a DC machine. We can start with a DC generator. Here we have an example. We have a permanent magnet inside a combination of coils, and as this permanent magnet rotates, it creates a changing magnetic field, which will induce a back EMF in the coils. If you then capture this induced voltage and current with an appropriate circuitry, we can create electric energy. And then, as we saw before, we can convert that energy from what would be here a AC to DC, and then back to AC at an appropriate frequency. So that's the principle of a generator. We create an alternating magnetic field from an external power source. And that alternating magnetic field is simply a magnet or a coil that is powered, that rotates inside a coil arrangement, a specific arrangement of coils. You have probably all used already brushed DC motors in your projects, and we always call them brushed DC motors. Does anybody know why we call them brushed? Now we have brushless and brushed. Well, what is the purpose of having brushes in a DC motor?
I think brushed motors have like a physical contact with the commutator ring.
Exactly. There is a commutator ring, and that commutator ring is there to ensure that the force is always developed in the same direction to ensure continuous rotation. We'll see later, if the commutators were not there, then force would, in half cycle, would be in one direction, in the other half it would switch directions, and the motor would not rotate continuously. So the idea of having these brushes and commutators is to switch the direction the coils are actuated depending on the orientation of the coil itself, to ensure that the force developed in the coil is always happening in the same direction, so ensure continued rotation with that. In a stepper motor, the orientation of the magnetic field controls basically the position of the motor, and the direction of the current. If we are dealing with a reluctance motor, doesn't matter. If you're dealing with permanent magnet motors, it will be controlled by the direction of rotation, will be controlled by the direction of current. In DC motors, the idea is slightly different. We have coils, we have a fixed magnetic field, and the coils will have to be switched direction to ensure that rotation happens in a continuous manner, as we just discussed in the previous slide. So you're going to see these applications today, and how exactly a DC motor operates, and what are the modeling and the equations that describe the behavior of the system. So before we go into that, we need to address two key concepts. The first one is the electromotive force in a moving wire. As we saw before, if you take a wire and you subject that wire to a changing magnetic field, or we have a fixed magnetic field and you make the wire travel in that magnetic field, in both cases, the wire sees a changing magnetic field over time. And as we saw before, this will create an induced EMF in the wire. And that induced EMF depends on the derivative of the magnetic field times the number of turns of wire that are exposed to that changing magnetic field. So we can say roughly that for one wire only, we have a changing magnetic field, a delta phi, divided by delta t, delta time, and this will create a induced EMF. Now let's consider the example here where we have this rod that represents a wire, It moves with a velocity v, and it moves at a velocity v through a magnetic field oriented upwards, as shown. It will move at a velocity v, and it has a length L. As it moves through that magnetic field, a back EMF or a EMF will be induced in that wire. If you now close the loop, a current will develop in the wire. Now let's see if you can calculate how much EMF we can get from this scenario here. We can describe the magnetic flux as simply the magnetic flux density times the area. We're going to call here delta A, or the area covered by a certain amount of time, that is delta T. How can you calculate delta A? Well, if we are dealing in a wire that travels, say, this distance, this is the area covered by the wire as it travels a certain amount. If it travels at a speed v and it takes t seconds to cover that area, this distance would be v times delta t. In that period of time, the speed of the wire times the time it takes to travel gives a displacement. If you now multiply that by the length of the wire, it gives us the red area. So this gives now B times V delta T times the length of the wire, all divided by delta T, which results in LV times B. This is the scalar version of this equation. This is the magnitude of the induced EMF. So it depends on three things. It depends on the length of the wire. It depends on the speed of the wire. The faster it travels, the more EMF it sees, and it depends on the strength of the magnetic field. This is the scalar version. We can also write that in a vector form where the induced EMF would be VL, where V is the speed, cross product B. Right, so these are vectors. The result of a cross product is also a vector, and this gives the direction of the induced EMF. In this case, we can use the right-hand rule. V is going to the right, B is going upwards, so the induced EMF points towards me. Right, V points that way, B points upwards, the back EMF points towards me. If you close the loop, a current will be developed and the current would be coming out of that wire. Right? So, because this is a cross product, we need to account for the variation of the magnetic flux, and this is accounted in the cross product with the VLB sine of theta, when theta is the angle between the magnetic flux, the magnetic field density B, and the speed V. That is to say, if the wire moves parallel to the magnetic flux, no EMF is created. If it moves at a 90-degree angle, then we have the maximum EMF being created, and if it moves on an angle, then we need to account for the sine of that angle. Right? This is simply the cross product. So this is the first concept we need. The second one is the Lorentz force. So going back here, if we close this loop and we provide now a path for a current to develop, thanks to that back EMF that is now pushing a current through it, this current will, because it's traveling on a magnetic field, will be subjected to a force. And this force is called the Lorentz force. In general terms, we can say that if a particle of charge Q moves with a velocity v in an electrical field E and in a magnetic field B, this particle will experience the following force as given in equation 4. Right? Q times the electrical field plus the cross product between the charge times V and the magnetic field B. In our case, we are not concerned with the electrical field. We can assume that to be 0. For the case of the wire, this simplifies even further. We can say that a current carrying wire will be subjected to the force I times the intensity of that current times the integral of dl, or the direction it moves, cross B, where B is, again, the magnetic field. Assuming that the wire is straight and that integration can be simplified to simply L times I, this wire will be subjected to this force, I, the intensity of the current, times L cross B. And again, we can use the right-hand rule to determine in which way that a current, that a force now will develop. In a scalar and a scalar factor, that would be simply IL B sine of theta, right, where theta is the angle between L, the length of the wire or the displacement or the path that the current takes, and the B is the magnetic field. So in this case here, in which way is the force? So current goes in, we have the magnetic field pointing upwards, so the force points to the right. So current, index finger, then you have middle finger pointing towards B, up, and then the thumb gives the intensity, the direction of the force. So this wire, if it has a current flowing inwards, it will experience a force going to the right. If the current is reversed or the magnetic field is reversed, then the direction of the force will also change. Okay, so these are the two principles, and you see where I'm going with this. The first one will be used to explain how a generator works, and the second one will be used to explain how a motor works. Let's get into that. Let's start with a DC generator first. Consider this case now where we provide a magnetic field using a set of magnets. We have a north and a south pole. These lines should be reversed. Actually, by definition, we go from south to north, but for the purpose of our analysis, it doesn't really matter. And we have then this constant magnetic field B. We have a wire that is exposed in that magnetic field, and now let's give this wire a velocity, a displacement. In the first case, we have a displacement pointing upwards, and you have a magnetic field that is orthogonal to it, and it goes like that. If you now create a path for this wire that is moving upwards, it will develop a current. And if you do again the right-hand rule, we do V cross B, we get the current going inwards. V points up, V is the middle finger, the index, then B is the middle finger, which means that the thumb points towards the EMF. So the EMF goes inwards, which means that the current will also go inwards if we assume that the current follows the back EMF. Now, if you do, if you reverse the speed, now the speed points downwards, you can apply the same rule. Try it at home, nobody's looking at you. You'll see that the current now comes out of that wire, right? And the polarity of the back EMF now switches depending on the direction of the current, or the direction of the motion. Any questions so far? Are these two concepts fine, and this one as well? Yeah.
Could you explain the hand rule again?
Yeah, so I have, so this is a right-hand rule for, here we are. This is for the force. So if you want to do a cross product between these three, we have I, B, and N, that gives you F. In the case of, if you want to calculate the EMF, this would be V, B, and the EMF. Okay, so the thumb points towards the first vector, the index points along the first vector, the middle finger, the second vector, and then the thumb gives you the third vector in the cross product for either, both cases. So let's go back here. This one, we have, first one is L, or the direction of current. All right, so that's inwards. Then we have B pointing upwards, and then you have the resulting force that points to the right. In this case here, the first one, we have V going up. We have B pointing that way, and then the results in the thumb pointing inwards, and that is the resulting EMF. All right. And in the second case, now try that, see if that works. The current should be coming out of the screen. Okay. All right, so now let's make a generator out of this concept. So we saw here that depending on how the wire moves, we have an EMF. Now let's take this wire, give it a loop, like the one in the figure, in the top figure here. We create a loop, and this loop now rotates at a given speed. If it rotates at a given speed, we can say that at this wire here, let's say rotates with respect to a center point here, this wire experiences this instantaneous velocity. And the second wire experiences this instantaneous velocity. Now you see that both sides of that coil are rotating in opposite directions with respect to the magnetic field. So the current that they generate, if you create a closed path, will be in opposite directions. Because we need a changing magnetic field, then we can say, we can make an approximation and count the number of magnetic flux lines that the wire crosses to determine the strength of the EMF it produces. That is to say that when the wire is flat at a 90-degree angle with respect to the magnetic flux, so we have the wires, let's say, like that, and this is starting to rotate, we see that it's crossing the highest number of magnetic flux lines. Hence, at that instant, the specific point in time, we'll have the maximum EMF being generated. Conversely, if we are now perpendicular or parallel to the magnetic flux in a configuration like this, then you see that at that specific instant in time, we are moving along the lines, even though it's a rotation. And at that specific point, the top wire and the bottom wire are moving parallel to the wire, along the lines of the wire, which means that at that specific point in time, the generated EMF is 0 at that specific point in time, because they are along the lines of the magnetic flux. They don't see any change in magnetic flux at that specific instant in time. This means that the cross product will be 0. Now we have VBL sine of theta, the angle between V and B would be 0, and it would create 0 back EMF at that instant in time. So now let's see. Let's consider this first part of the wire here. This first part, if you apply the right-hand rule, we'll see that the current will be flowing in that direction, because V, the component of V that is along the magnetic path, goes like that. In the second half of the wire, we see now that V switched directions and is now pointing, the component of V along the magnetic flux is actually pointing in the other way. So immediately we can infer that the current will flip directions. So as one part of the top wire, say, is creating a current that is counterclockwise, the bottom part creates a current that is counterclockwise, but they are in the same loop. So they can eventually they create a current that goes in the same direction. Let's assume now that this coil is, let's say, like that, flat, and it rotates like this, right? So for the first half of rotation, we have this happening, and you haven't reached the point of 0 back EMF, so the current flows in one way. Now when we pass the point of 0 EMF, and you're now in the second half, we see that both sides will flip direction, which means that the current itself will flip direction. The current itself flips direction on both sides of the wire simultaneously. So when you pass this point of 0 back EMF, the current changes. If you now attach 2 wires to this loop and plot the resulting EMF, we should see a sinusoidal waveform as we see here. Now it creates a AC voltage. Well, this AC voltage is used for certain applications, but if we, the frequency strongly depends on how fast this rotates. And so as you saw before, to have more control over this voltage, we can rectify this voltage and create a DC voltage instead. So one way would simply be to put a rectifier here and do that with diodes. But you can also have what we'll call here a mechanical rectifier, which is actually the commutators in the loop. So in the commutators, we'll have each coil that is, instead of being attached to a ring, it will be attached to a ring that is only 180 degrees. So let's say this ring goes like that for 180 degrees, and is connected to the coil. And then you have a secondary ring for the other part of the coil like that. And then you have two collectors on this side that are pushing against these rings. They are not fixed, they are pushing against the rings. And what happens now? If we do this properly, when the current changes direction, the commutators will also flip direction. We are basically connecting the collectors to different poles of this multimeter. This means that from the multimeter's perspective, we should always see current flowing in the same direction. As soon as the current flips direction, as soon as we pass the 0 EMF mark, we flip the orientation mechanically. We are flipping the orientation of these collectors. So we flip the way the voltage is measured. And the voltage is then measured from this multimeter's perspective, always in the same direction. And that's the role of these commutators here. They typically have carbon connectors with little springs that push against moving rings. These rings that are, in this case here, each ring would be 180 degrees. So if you only look at the voltage that is coming out of the wire, this is what you should see, because the current is constantly going back and forth. But if you now use the commutators at 180 degrees and we place them properly, align them properly, this is what we should see. As soon as the current flips direction, we also flip the way we measure them. We measure the current, and then the voltage is now rectified mechanically and is always positive. Okay, is this clear? Is this rectification, mechanical rectification, clear?
Question.
Yeah.
So, sir, the reason why it turns in the second graph as to all positive is because of those rings?
Is because because of those rings. So one side, let's say the red side is fixed to one side of the coil. The purple side is fixed to the other side. So you have this then two collectors that are pushing against the rings. They're not physically connected, they're just touching the rings, right? So in the first half cycle, let's say before the back EMF is 0, the red one, let's assume it's creating a positive voltage. As soon as it passes now to the other side of the 0 back EMF, it would create a negative current. So the first half positive, the second half negative. What happens is that when you flip to the second portion, now the red one would be connected to the other side of the commutator. It would be connected to this portion here. From the first half cycle, it would be connected to the left one, and as soon as it passes the 0 degree mark or the 0 EMF mark, it now connects to the one on the right side. So as soon as the current flips, we also flip the way it is connected. So you read the current always in the same direction. Does that make more sense?
I think so, but I don't understand. So when you're saying the back EMF is 0, we're physically moving the wire or rotating the wire?
This wire rotates like that. Right, so if you look from the front at a cross section, this is what is happening to the wire. It's going in a circle like this from one wire. And this is the other wire. So they are rotating inside. Okay, along this axis. Let's put an axis here. So it rotates along this axis. Yeah.
Is the goal to only have a positive voltage?
Is it? I didn't catch it.
Is the goal to only have a positive voltage?
Yes, the goal is to only have a positive voltage. is to have a DC voltage coming out of this. Any other questions? No? Okay, so if there are no other questions, let's move on. So now if you look at our rectified voltage here, this doesn't look like a DC voltage at all. It's more like simply a rectified sine wave. How would we go about creating a more smooth DC voltage in the output? Any ideas?
You could use a filter.
We can use a filter. Yeah, we can definitely use a filter. What else could we do in the motor side? Let's say, let's not add any electronics, just on the motor itself.
You put
How could we
in there at a phase shift, basically.
add a phase shift? We can add another coil. We can add another coil and make that coil shifted with respect to the first one. You see, there are points in this system where the coil doesn't produce any back EMF. So there is no point in keeping contact with the coil when it doesn't produce any back EMF. So what it could do is to add a second coil here. So then I have a second coil that is, in this case, 90 degrees out of phase with respect to the first. And now it has its own commutators as well. So the commutators before had each 180 degree range. Now they have a 90 degree range. 90 degree range where they make contact with the collectors, with the brushes here. Right. So we only take the current out of those out of those loops for 90 degrees at a time, and then you switch to the other coil. What happens mechanically is that electronically, now we have a AC signal that is also shifted by 180 degrees. So each of these, by 90 degrees. So each of these here, these two will come from one of these coils. And what is the resulting EMF? Well, the resulting EMF is going to be something like this. This is what we see in the resulting EMF. It's just the peak, right? Because we are switching between the blue and the red one. We now have something that resembles a DC current more, and we can keep increasing the number of loops in this arrangement, right? So to create something that resembles a DC voltage more and more. That's one way. Another way is to add more magnets to create a smoother magnetic field like that. That's another option. And we can, of course, combine both arrangements, have more coils, more loops, more commutators, and just one collector, but now have more magnets to ensure a smooth magnetic field. Okay, so that's the principle of a generator. The induced EMF here will depend on intensity of the magnetic field. It depends on the speed of the conductor with respect to the magnetic field. So it depends on how fast, in this case, this rotates, the angular speed of the conductor, and the length of the conductor as well. Of course, the number of turns and so on. Okay, here we have just one turn, but each coil could have multiple turns before it returns to the collectors. Okay, so that's for the generator. So in the generator, we apply a mechanical power to move the inner part of to move the coils. According to this law that the induced EMF is applied, we can now rectify this voltage and have a electrical power coming out of the system. Now we can go the other way. We can apply an electrical power to the system and reverse the process and create a mechanical power. So in this process, we are going to use now use Lorentz law for the force being created. Now the input is an electrical power. Because these wires will now be subjected to a force, they will rotate, and we get out a mechanical power out of the system. So DC motors, we have a current as input and output a mechanical power. Generators have a mechanical energy as input and output a DC power, a DC current. Right, so now let's go through the second way here. Now we're going to go back to the second concept, where a wire or a conductor carrying a current experiences a force that is given by I times L cross B. The force depends on intensity and direction of the magnetic field, the length of the wire, and intensity and direction of the current. So let's see the first case here. In the first case, we have this wire. I'm just showing a 2D representation of the wire that is coming out or going in the page. We have a magnetic field pointing to the right. And according to the right-hand rule here, if the current in this arrangement is coming out, we have a magnetic field. So the current points towards me. We have a magnetic field pointing towards the right. So the force, according to the right-hand rule, will be pointing up. How can we explain that? Well, remember that if there is a current coming out, the current comes out of the wire. We remember from lecture 2 that we can also use the right hand to determine which way the magnetic flux rotates. The magnetic flux, in this case, to have a current or a coming out, will have to be rotating counterclockwise with respect to the wire. So if we have a magnetic field, again, going counterclockwise, that means that the current comes out. Which means that the direction of the magnetic field spinning around that wire is counterclockwise. The magnetic field from the magnet points to the right. So what happens? At the bottom here, we have the magnetic field from the wire and the magnetic field from the magnets, both pointing in the same direction. They have the same polarity, so they will repel each other. On top of the wire, though, we see that the magnetic field from the wire and the magnetic field from the magnet are now in opposite direction. So they will attract each other, and that's why the force goes up. Let's see the second case. In the second case, the current goes in the page. If the current goes in the page, we can do the right-hand rule again. So I goes in. What is this? This is B, and then you have F pointing downwards. So if the current is going in, we can say that the magnetic flux for the current to go in, we have to rotate clockwise. Now the top of the wire has both fields pointing in the same direction, so they will move away from each other. The bottom has both fields opposing each other, so they will attract each other, and now the wire experiences a force pointing downwards. And this is what we're going to use to create a motor. Now what you'll have to do here is to apply a voltage to this wire, and the wire will move up and down. I had a demo to show during live lectures, in-person classes, so unfortunately we can't do this today, but you can do an experiment at home. You can have a simple magnet, and you have a wire, like a loop of wire, connect the wire to a battery, and you see that immediately the wire will move up, and if you reverse the battery polarity, then it moves downwards or the other way. And that's based on Lorentz force. Now let's create a motor out of that method. How do we do a motor? Well, same arrangement that we had before, but now the input to this is the electrical power, not the mechanical power anymore. We had before a mechanical power rotating the wires like that. Now we're going to apply a voltage to this wire, and we expect now this wire to rotate in a given direction. But here we're going to run into the same problem. Half of this loop has a current, let's say, in one direction, the other half in the other direction. So for this instant in time, a specific instant in time, the forces on each side of this wire are in opposite direction, so they will create a torque in the same direction. That's good. They create a force that in opposite direction, the torque goes in the same direction. Because again, the component of the current and the component along the magnetic field will change. In top part, the bottom part, the component of the current, component of the force along the magnetic field is in opposite direction, and the top part is in the same direction. So as soon as we reverse that, the force will change. We reverse the current, the force will change sign. So the force on the top goes that way, the force at the bottom goes that way. That creates a torque in the same direction. But again, now, when you pass a point of 0 EMF, what happens to the force? If you pass this point of 0 EMF, what happens to the force? The force flips on both sides. So here at this instant, the force creates a torque that is clockwise. As soon as we pass the point of 0 back EMF, now the relation between the cross product between the current and the magnetic field on both sides of this wire will change direction and will create a force. Now the forces on both sides will flip, and that would create torque in the counterclockwise direction. So that doesn't work as a motor, because as soon as we pass the point of 0 back EMF, now the force points in the other direction. So how do we fix this issue? Let's add our commutators again. But now the commutators work as a way to reverse the voltage we apply to each side of the coil, and make sure that the current always creates a force in the same direction. So as soon as we pass the point of 0 back EMF, now one commutator is touching the other part of the collector, these red pins here, and the current is reversed. So if the current is reversed exactly as we pass the point of 0 back EMF, the force also reverses, and the force then continues to occur in the same direction and creating a force in the same direction. It's the same idea that we had before to generate a DC current. Now we apply the commutators here to ensure that the current is reversed exactly when we pass through the point of 0 back EMF. So the force generated through that current creates a torque in the same direction all the time. Okay. There is a point here where there is no force, there is no torque, and that's again when we pass the point of 0 EMF, no current, no force. So to ensure a continuous torque across this rotation, we can add more wires, more commutators, and then simply activate those that are close to having close to the point of max back EMF, which would be here, right, to create the maximum torque. All right. Any questions here?
So just a quick question.
Yeah.
When we're working with DC motors and we're working with, say, the encoders for DC motors, is it looking at every time it sort of switches from one wire to the other is when we get it's
no,
not
no, the encoders are there for the purpose of measuring position for something else. The motor itself inside has a mechanical connection that will ensure that it changes polarity. Let me try to explain this one more time, because it seems like it's not very clear. So let's say this is one side of the coil, this coil here. So you have one commutator, and here we have another side of the coil. Right, so both go to the coil like that. And they are rings, they are metallic rings. And then you have these parts that are pushing against the rings, and they are connected to a DC source, for example. Right? And let's say that our DC source is this way. That creates a current going like that. Right? So in this example here, the current, let's say, would go through this and back like that. Right? And in this instant in time, let's assume that the coil would create a torque in the clockwise direction. As soon as the coil passes the 0 degree mark, and if you apply the current is still in the same direction, we all agree that the force would change the direction. Right? So how do we fix that? Well, to make the force now go in the opposite direction, we need to reverse the current. How do we reverse the current? It will automatically reverse, because when the red part rotates and the system becomes like this, now it rotates, let's say 90 degrees. Now you see that the current is going in through the red part and is coming out through the blue part. We reverse the current mechanically from a DC source. And this is very timed with the point of 0 EMF or of no torque. All right, so these green parts are pushing against the rings, and as the ring rotates for half of the cycle, current goes in from the blue. For the second half of the cycle, current goes in from the red. Right? And it will do that. It will switch when you need to switch the current to ensure that the force goes in the same direction, right? So this is mechanically implemented in a DC motor or a generator. It's not any, the encoder serves a different purpose. It's for control or speed or position measurement.
Okay, so and if we wanted this an even smoother torque delivery, we would use just more and more of those coils.
More of those coils with their respective rings.
And that's how we end up with the brushed DC motors with like a lot of commutators.
Yes, exactly.
Okay.
Now, if you open a DC motor, we'll see that there's a bunch of commutators like that. You could look at the shaft, and that's what it looks like.
Question?
Yeah.
So for the previous one, before it changes direction, there is no rotation from the commutators?
What do you mean by there is no rotation?
You said they switch once the direction is switched, right? Once we reach the point of zero EMF.
Mm-hmm.
So before that, are they just like stable but pushing? But then like after the 0 point is reached, then they switch direction? I'm not sure if I really got the point here.
I'm not sure if I understand the question. When you switch direction, exactly, let's say in this point here, when the commutators rotate like that. And passing that point, now you see that the red one will touch the right, the blue one will touch the left. We arrange that in a way that this will occur when we pass the point of 0 EMF. I think about these two wires, this blue and the red, rotating. You see that for this rotation here, if you do another 90-degree rotation, the blue is still connected to the right one. Past 90 degrees, now the red one touches the right one. That's how the commutation occurs.
Okay, yeah, I get it. Thank you.
All right, so now let's complicate things slightly. Why use a permanent magnet? We know that we could simply use a secondary coil to create a magnetic field. In this example here, we have two cores, one of each side, and they have a coil wound around this magnet, these ferromagnetic parts. If you now apply a voltage to that coil, that creates a magnetic field and works as an electromagnet, works as a permanent magnet. So there are two arrangements here. The first one is the series connection, where we have a DC supply going through the core, creating a magnetic field, and then going through the commutators, and coming out of the other side and doing the same. And we have the second example where both coils here, the coil in the rotor and the coil in the stator, are now connected in series with respect to the DC supply. So you have one coil going to the motor, one coil going to the stator to create this permanent magnetic field. They can be connected in series. They call that series wound or shunt wound for the case where they are connected in parallel. So this makes the arrangement, the fabrication easier because you don't need permanent magnets. And typically the big motors that you see, big DC motors or AC motors, they will actually follow this configuration rather than having a permanent magnet inside. Another advantage of this is if you work with this system as a generator, you can control the intensity of this magnetic field through how much power you deliver to the stator coil. And now we can create, we can adjust the output, electrical output of the system to always be a constant, at a constant voltage. So you basically actively control the strength of the magnetic field to ensure that the output of the generator is always at the same level. In the case of a permanent magnet, the only way to do that is to control the speed. But if you think about a turbine or wind turbine, for example, you cannot do that because the speed is constant.
Question.
Yeah.
Is there an advantage between series versus shunt connection?
Not necessarily. The second one will provide more control because you can independently control the voltage. I don't see. I would say maybe the advantage would be the controllability of the second arrangement, because you can control both currents independently, where the first one, the current that flows through one coil is the same as the other coil. So maybe it's easier to build. That's my guess. But the second one offers you more flexibility to control both. But that's a guess, I think, from what you see here. I believe that the second arrangement would be more used than first.
Question.
All right. So yes.
I just wanted to make sure of something. So when the coil turns clockwise, and then after the point of EMF, and then it's like everything happens, and then those circular things, I forgot what they're called. So they switch. Does that affect the polarity of the DC motor? Does that flip too?
What do you mean by the polarity of the DC motor?
So when you were explaining earlier, you were saying that after the point of back EMF, they those circular thingies, they flip direction. So does that mean it just one of them stops bringing in power from the DC motor?
No, they don't flip direction. They flip the direction of the current. These things are rotating. They are fixed and they are rotating. They are always at the same position with respect to one another. During half of the cycle, the blue touches the right. During the other half cycle, the red touches the right. When the red touches the right, the blue touches the left. They flip because they are rotating. The current going in the motor changes direction. Okay. Right? They are always fixed with respect to one another. They're just rotating. Well, when they say they flip, the right one, the blue one touches the right collector during half cycle, and during the other half cycle, the blue touches the left connector. When the blue touches the left connector, the red one will touch the right one immediately, and they stay along that for half a cycle each. If that's not clear, I can try to explain that during office hours in more detail. So now let's look at this circuit here. We have a series or a shunt arrangement, and you want to characterize this system. So what you can do typically is to rotate the machine at a constant speed with an external supply, change the current that we pass through the secondary winding here, through the stator winding, and measure the induced EMF at the rotor winding, and then plot that. And this is the plot we see. As we increase the strength of the current in the stator at a given speed, as it rotates at a given speed, the voltage that we read across these collectors will now increase in magnitude. It doesn't increase linearly because there is saturation of the ferromagnetic core. Right? The relation between I and B is linear for a certain amount of, for a certain range, and past that range it becomes nonlinear. That's why we see this curve being nonlinear. Now let's move on to a little bit more on the characterization. Let's try to calculate the induced voltage in the winding. We know that the induced voltage in the winding is going to be proportional to L times B times the speed. If this rotates at a constant speed omega, constant speed V, we know that a V at this specific point here would be the angular speed times the radius of that wire. Right, so that's the omega R. Angular speed times the radius gives the linear speed of the wire. We see also that we have a number 2 here because each coil now has 2 loops. If we have P poles or pairs of north and south poles here, we can calculate the area exposed to the magnetic field. we can calculate this by assuming, for example, that we have a perfectly cylindrical configuration. This would be the radius, this would be the length of that rotor. What is the area? Well, the area is this entire surface that passes through the magnetic poles. If we have p poles, well, the area is simply 2 pi times L times R. That is the entire area of that cylinder. If you divide that by the number of poles, that gives us the area of one pole, the area exposed to the magnetic field to one specific pole. What else can we do? Well, we can calculate, expand the equation on top here as a function of the magnetic flux density. We know that this is phi divided by A, where A is what we just calculated there. So we can now replace, I'm going to do these equations a bit fast, but you can double check this later. What I'm doing here is simply dividing phi by A to get B. This would go in B here, and A is this, A goes there. And then when you combine all these equations, this is what we get. The EMF that depends on the number of poles, depends on the speed and the max magnetic flux. And pi here is simply a constant. If the armature now has n turns, this is just for one turn. If the coils have n turns, then you simply multiply that by the number of turns in each pole. So if you have p poles, this is the number of turns exposed to a pole. So that equation 8 times n time divided by p gives the total EMF in the circuit. And when we expand this equation, this is what you're going to see in the output. N divided by pi times phi, the magnetic flux, times omega, the speed. And this is the EMF constant, or the speed constant that we used in control systems. We saw that in control systems, the back EMF would be a constant times the speed. This constant in control system would be this 3 here. The number of turns divided by pi times the maximum magnetic field phi. In this course, we assume that these are characteristics of the motor, and this is in fact the constant. The speed constant is n divided by pi. All right. So the faster you rotate, the more EMF we get. The greater the magnetic flux, the more EMF we get, and that depends on that proportionality constant from the speed to EMF is n over pi, and that's Ka. That's the speed constant in the DC motor. Now let's do the same analysis to see the torque. We'll do the same, but now the only difference is just give me 1 second. There. Now the difference is the starting point. The starting point now is the force. If you calculate the force along these wires and multiply that by the radius of the wire, that will give us the force perpendicular to the wire and multiply that by the radius, that gives us the torque. So we can start by calculating the force as B times L times IC. If we have P poles, if we have a current going in, so the total current going in is is capital I, then we have I divided by P is the current through one coil exposed to the field at a time. So IA is the total current, we divide that by the number of poles. Then we have that divided by P is the number of the effective current through one pole at a given time. We can follow the same idea we had before. We will replace B with the expression we had previously, phi divided by A, but now this is multiplied by L times IC. And you can continue development. I will let you go through this derivation later, but it's the same we just did previously. It's just now the starting point is slightly different. If we have n conductors, each conductor will create a force in one direction, hence this number 2. And you have n conductors, that is n here. It's not n divided by p because you already accounted for p on top there. And the total torque now depends on K times phi times the current, right? Or, okay, this is, I think there's IA missing here. IA missing there. So what do you see here? We see the same thing that we had before for the other, n divided by pi, that's Ka, same constant, times the magnetic flux, but now times the current. So the torque becomes proportional to the current. Same we did in control systems. We saw that the torque was K times the current. And is what we see here. That's where it comes from. It's a constant Ka times the magnetic flux times the current. So assuming that a Ka and the magnetic flux are fixed, we can say that now the torque is proportional to the strength of the current flowing in the rotor. And that's where this proportionality constant comes from. Another interesting observation that we see here is that this torque constant is the same as the speed constant. Theoretically, they are exactly the same. Now, if you buy a good motor and you look at the data sheet, they will be exactly the same. One is in Newton meters per amp. The other one would be in volts per radians second, right? To give you radians per second. If conservation of energy in this system applies, then we can say that the electrical power input terminal current times the EMF is equal to the power delivered in the motor, a torque times speed, if conservation of energy applies. All right, so let's do a little bit more on electromechanical modeling before we do some examples. So here we have this motor from control systems. It's the same model, so I'm not going to go through all the details. Again, this should be relatively fresh as you just took control systems. We have the electrical and the mechanical part, and now we're going to try to link them. We can have an armature voltage that is represented, an armature circuit that is represented by this portion here. So the resistance of the winding and inductance the winding, and we have a back EMF that here is represented as a power source. We can do Kirchhoff's law. So we have V equals to the current drop through the resistor, through the inductor, and the back EMF. And when you take the Laplace transform of this, we have Vs equals to I of S times R plus Ls I of S plus E of S. We can create a transfer function for the current, and that would be simply rearranging the elements there, factoring out I. This gives a transfer function for the current as a function of the EMF and as a function of the input voltage V. Nothing extraordinarily new here. We know that the EMF is K times omega, so we could rewrite this as V of S minus K, sorry, no, K times omega of S divided by Ls plus R. And this is the link between the mechanical and the electrical part. We can now go to the mechanical part and write the same. So we know that the sum of all torques is equal to the moment of inertia times the acceleration, angular acceleration, which here is represented as the derivative of the speed. And all torques acting on the system are the torque provided by the electrical part minus friction minus the disturbance torque or the load torque being applied to the motor in opposite direction as that of the motor itself. We can take the Laplace transform of this. What happens? We have T of S minus TD of S equals to omega of S JS plus B. Again, from control systems. which means that the transfer function for the current, for the speed is T of S minus TD, which is the disturbance torque divided by JS plus B. And here we know that at T of S, the torque is simply K times the current. And again, the link between the electrical and mechanical part show right there, through the current this time. All right. So this is from control systems. Now let's do a block diagram. If you take all these equations together and rewrite our transfer functions, we can create a block diagram for the motor. Let's start this block diagram where the input is. The input is V of S, is the input voltage. If you take V of S and subtract omega times Km, the torque, the speed constant, what is left? We have the top of that equation. If you divide the top or divide that equation by 1 over, multiply that by 1 over Ls plus R, what is the output here? What is the output there?
IS.
IS, exactly. So this is IS. If you now multiply IS by the torque constant, we get the torque. Right, let's call this Ki to be consistent, Ki. That's the torque or current times Ki. This is exactly this element here. We now subtract Td from it. That gives the top of this equation. Divide that by Js plus B, gives us the speed. Integrate the speed, gives position. And now we can close the loop here. Notice that we need omega times Km. Right, so omega we take from there, and Km is the motor speed constant right there. Okay, nothing new. This is again all from control systems. Now let's try to redo this block diagram. Let's try to do the block diagram without any transfer function, just with constants. How would we do that? Let's try this one. So these are the equations for the motor, for the speed, and for for the mechanical and electrical part, and we can attempt to do this without any transfer function. To do that, we need to isolate the highest derivative, and the highest derivative that we show in the equations we just calculated is basically Lis times S. We can start from the input in the first equation and create an expression for this element with the highest derivative. That would be V of S minus omega Km, we'll find this later, minus I times R. The resultant signal here is Lis times S. All right, so these two sums give this side of the equation. And the output is L times Is times S. If we now multiply this by 1 over L, we get Is times S, integrate, we get Is. We needed I times R, so just multiply the feedback loop by R and you get I times R. So that's done for the electrical part. Now let's do the mechanical part. Mechanical part, we can input the disturbance torque, Td, is subtracted from the torque itself, which is T of S, which is the same as I of S times Ki. We subtract from that something like omega B that we'll find later, and this would give the result of that sum would give this side of the equation, which is equal to J times, so this point here is J omega S. Multiply that 1 over J gets omega times S, so the acceleration. Integrate gets omega, integrate again gets theta. We needed a feedback loop with omega times B, so simply connect that to omega, multiply that by B. Now what happens here? We need on the top here, we need I times Ki. So we have Ki, that multiplies I that we can take from the top. And at the bottom one, at the other one here, we need omega times Km. So multiply omega by Km, that's Km, and omega can be taken from there. And this is the same block diagram representation, but now without using any transfer functions. Okay. I rushed through these block diagrams because I think it's fair to assume that this is still fresh, given that we just took control systems. Another last concept that I want to introduce today is the concept of nominal current and the stall current, or no load current and stall current. And stall current means the maximum current the motor creates at rest when there is no speed, it's not rotating. If there is no speed, then you see that this feedback loop here is basically sending 0 back. And the current that was initially V minus E divided by Ls plus R now simply becomes V over R in steady state. Typically, the resistance in a motor is very small, is in the order of a few ohms. So if you apply 100 volts to a motor and have a resistance of 1 ohm, that's 120 amps going in when the motor does not rotate. Multiply that by Ki, that gives you the no load, or the stall, gives you the stall torque, the torque at no speed. That torque cannot be sustained for a long period of time because it will simply burn the coils. It's not designed to handle that amount of current. But it only occurs when the motor has no speed. It's at rest. And that's exactly why when you turn on a motor, you see a spike in a current and then it slowly decreases, because then the back EMF, as it starts to rotate, kicks in, and then this relation here will make the current drop. The other one is the no load current. When we turn on the motor, apply a no load to the system, there is a current developed in the motor. That current creates a torque. Where is that torque going? Let's assume that we turn on a motor, the motor starts to spin and eventually reaches a steady state speed. And you look at the current, there is a current going in. If there is a current, there is a torque. The motor is not accelerating because it has reached a steady state speed. What is that torque doing? Where is that torque going? What is counteracting that torque?
Can you hear me?
Yeah.
Isn't it like the natural weight of the, what do you call it? I'm just gonna say like the natural weight of the actual motor itself.
That would be more the case, I think, with the generator. With the generator. In this case, it would be friction. As the motor starts to spin, there is friction, and friction creates a torque B times omega. So at no load, if there is torque, the torque is simply there to overcome friction so that we reach a steady state. So we can say now that the no load current times a constant times the current constant is equal to the frictional torque in the motor. Right? So a stall current, the maximum current, before it starts to rotate, no load current, the current that it develops to simply overcome friction due to its rotation at no load. Right? I think the answer I just heard had to do more with the generator, because as we spin, there's a force acting against motion, right? Because of Lorentz law that would indeed apply there. Here it would be more related to the motor friction itself.
So it was B in here is friction, right?
B is the coefficient of viscous friction.
Oh, thank you.
All right, any questions, any other questions?
Quick question.
Yeah.
When you say no load, the load is referred to a physical load? Like there's no applied torque, there's nothing, like you're not holding on the shaft of the motor. Okay.
Exactly. Yeah. Okay, so any other questions, or can we do some exercises? All right, so let's try to do some exercises. I went over time once again. All right, let's do exercise 59, and then I'll try to do exercise 60 if we have time. We probably won't have time, but it will go over time and just do one exercise for the record. So let's start with this one. We have a 4-pole DC machine with an armature radius of 125 millimeters, a length of 250 millimeters. The poles cover 75% of the armature. The windings consist of 33 coils and 33 slots, each with 7 turns. The average flux density under each pole is 0.75 Tesla. We are to calculate the armature constant, the induced EMF at 1000 RPM, and the torque when the armature current is 400 amps, the developed torque in the armature, the power developed in the armature. Okay, so I'll let you read this one more time. And the first thing we need to calculate here is the armature constant Ka. So we have a 4-pole DC machine. We have the length of the rotor, 125 and 250 millimeters. 4 poles, each cover overall covering 75% of the rotor itself. We have 33 coils and 33 slots, each with 7 turns. So first, let's calculate the armature constant Ka. So how do you calculate Ka? Well, Ka is simply the number of turns divided by pi. Ka is the armature constant, both the speed and torque constant. So how many turns we have? We have 7 turns, and you have 33 coils. We have 33 coils with 7 turns each. So we have 33 coils, each with 7 turns divided by pi. This gives a torque constant of 73.53. If you talk about torque constant, that would be Newton meter per amp. If this serves as the speed constant, it would be radians per volt second. And both units, because these constants are the same. So that's for A, very simple. Now let's move on to B. The EMF, the back EMF generated when the motor rotates at 1000 RPM. What is the equation for the back EMF? The equation for the back EMF would be E equals to K times phi, the flux, times omega. How we calculate this? We have omega, we have the speed, we have K, but you don't have the magnetic flux. So how do you calculate the magnetic flux? We have the magnetic flux density as 0.5 Tesla. So to calculate phi, what do we need?
Area.
What? The area, right? We need the area of each pole that is acting on the system. So what is the area of this rotor? We can define the rotor as a cylindrical, having a cylindrical shape like that, and a radius r and L. What would be the area here? The area would be 2 pi r L, so it's the surface of that cylinder. Is the surface of that cylinder. Because we have 4 poles, what is the area of each pole? Is that divided by the number of poles. And because the poles only cover 75%, then you multiply this by 0.75. Is that clear? All right, the area, the total area here is the top divided by P, the number of poles, gives the area of 1 pole. You only cover 75% of the area, actually, according to the question. So we have 0.75. So this gives the area as 2 pi times the radius is 0.125. The length is 0.25 divided by P, which is 4 poles, and times 0.75. This gives an area of 36.8 times 10 to the negative 3 meters squared.
Just to confirm, so that being 75% means like 25% of the area of like a cylinder is just open space between those.
Yeah.
Okay, thanks.
Yeah, you can see kind of here,
Yeah.
right? This part, this little part here has nothing. There's no flux. All right, that's accounted in the 75%.
Awesome. Yeah, thank you. That makes sense.
All right, now we have everything. We have A. Yes, go ahead. And we have B.
So since we've divided by 4, does it mean that the E we're calculating is just for one pair? Like the
No, the E is the total, because only one coil is expected to be generating at a given time. You are not taking voltage from all coils at the same time. We are taking the voltage from the coil that is at a max through the poles, assuming that the other coils are not, right, because of the commutators. So the assumption is that we are taking only power from one of the coils, right? Hence the divided by P here.
Yeah, makes sense. Thank you.
Okay, so now we can calculate the magnetic flux. What is the magnetic flux? Is B times A, right? B is phi divided by A. So E becomes, what do you have? K is 75. Sorry, K is, where is K? $73.53 times 0.75, this is B, times the area, this would be A, so this is phi, times the speed. The speed is 1000 RPM, which in radians per second is 2 pi times 1000 divided by 60. Which gives a EMF of 212.5 volts. This is supposed to be a number 5 here. There it is. Okay. Are we good? Any questions? No? All right, so if there are no questions, let's move on to C. C is the torque when the armature current is 400 amps. How do you calculate the torque in this system? Well, we have an expression for the EMF that we calculated here. We can calculate the torque in the same way. Is K, same K, in fact, times phi, times EMF proportional to speed, torque proportional to
current.
All right. So it's the same that we had down here. K is the same, phi is the same. I'm not going to repeat the numbers, as these are the numbers, same numbers. And then the current is 400 amps. All right, the current is 400 amps. This is the current through all poles. What is the current through one pole? It's 400 divided by 4. All right, this 400 is the current going in, but you are splitting that current into four poles, hence 400 divided by 4. So each pole is subjected to 100 amps. All right, each pole is subjected to 100 amps. So T gives 811.8 Newton meters. And finally, the power in the armature. What is the power developed in the armature? Two ways to calculate the power in the armature. We can say that the power is simply the torque times the speed, which is equal to, yeah.
Was that value divided by 4?
Yes, this is a number 4, number of poles.
If I divide it by 4, I get 200.
Where you get 202? Here you get 202?
Yeah.
Yeah, all right. All right, so that's 202. Thank you. So now let's move on to the power. The power is the mechanical power, which is equal to the electrical power, the armature voltage, the back EMF, and the armature current. So these are equivalent. If the conservation of energy holds, we can use either. Let's do the mechanical. The mechanical power would be the torque, so 202.8 times the speed, so 2 pi times 1000 divided by 60. This is torque, and this is the speed, which should be equal to the EMF, which was calculated before here, 212. 212.5 divided by times then the current 400 divided by 4. Can somebody calculate this for me, please? In the meantime, let's do lecture exercise 60. We have a DC machine that is connected to 100 volts DC supply and is operated as a DC shunt motor. And no load, the motor runs at 1000 RPM, and the armature takes 6 amps. A potentiometer R is used to regulate the speed. So we see two important pieces of information here. We have the armature itself, and you have this curve that it gives the relation between the applied voltage in the core, the applied current in the core, and the measured EMF as the motor rotates at this speed. So it has a constant speed. As you start to increase the current, we see the system is originally linear and then it becomes nonlinear probably because of saturation. So we have this arrangement, 100 volts DC supply here. We have 6 amps coming through the motor, and we have this is the field voltage going through the armature winding, and here is the relation between what we measure here and this current at this constant speed. And then we have some things to calculate there. So let me erase the light board, and then we'll get it started with that. It starts with the resistance R. So what is the purpose of that resistor R? You see that as the resistor R is put in series with the armature winding, with the field winding, as we change R, we are changing the current through that coil, which means that if we change the current through the coil, we change how much voltage we can read in the DC, in the output. Because you see, this is the current through the electromagnet. By changing R, we change this current. And given that this is rotating at a 1000 RPM, then you're going to read a different voltage here. So R is a way to control, is a variable resistance that is a way to control this voltage read here at this constant speed. So by adjusting R, if the speed eventually changes, we can change R to keep always the same voltage being read at that specific point. So we have these specifications. Now the question asks, for this configuration where we are taking 6 amps here and 100 volts being applied right there, what is the resistance R in this particular arrangement. We can have two loops to solve for this. We have two parallel loops. We can do a loop here. It's called a loop 2. And you can have another loop, a closed loop like that. Let's call this one loop 1. Loop 1. Like that. And you can do Kirchhoff's law now to figure out the balance of voltages in here. Let's start with loop 1. What can you write for loop 1? We can write that a V, 100 volts, is equal to this resistance times the current. So IA times the resistance plus the back EMF. Plus the back EMF. And that gives E equals to 100 minus 6 amps. This is the current flowing through the motor right there, times R, which is 0.1. This gives 99.4 volts. 99.4 volts being generated here to limit the voltage, so to balance the voltages. All right, so if we are rotating now at 100 RPM, we can look at the graph and infer what is the voltage required here, the current required through there to get this exact back EMF. And from the graph, what can we say? So we are creating 99.4 volts at E. Remember that this graph was generated by rotating at a constant speed and changing the intensity of IF. And then we read the voltage E here. At 99.4, we can trace a line from 99.4 around 100 and down. We should be around 1 amp. Starting at 99.4, so right there, and then down, that gives around 1 amp for IF. This goes down, sorry. So for this, from the graph, it would require an IF of approximately 1 amp. Approximately 1 amp. Now we can go to loop number 2. Now that you know what current flows here, we can go to loop number 2 and do another balance of voltages there. So loop 2. What is the equation for loop 2? Give me the equation for loop 2, Kirchhoff's law, for a steady state condition. What do we get? We have this voltage here is 100. So if 100 is applied here, it's also applied here, it's also applied across these 2 points. So V equals to I times R, this R, plus I times 80, this 80 there. So the voltage is current times R plus 80, because this branch is in parallel with 100, it's also 100 volts, times 1, that's the current, R plus 80, gives R equals to 20 volts. Right, that's the voltage. That's the resistance that is required to balance the motor like that. So this is This is all for question A. Yeah, did I hear a question?
Yeah. Did we take into consideration that 6 amps? That's
yes, the 6 amps were considered here
not
to
in loop
calculate
2.
that. Yeah. So if we add this 6 amps times 0.1 plus the voltage here, we go back to 100 volts. Right. So on this side of the equation, I could have written 100 volts or 0.1 plus E. It's the same. It's all in parallel.
Okay.
Any other questions? No.
Question.
Okay. So yes, go ahead.
Should that be R equals 20 ohms? You have R equals 20 volts.
Yeah, that doesn't look right, does it? So that's 20 ohms.
Okay, thank you.
Yeah, thanks. So for B, we have the mechanical power at 1000 RPM. What is the mechanical power at 1000 RPM? The mechanical power, if conservation applies, is the same as the electrical power, which is E times IA. IA is the one flowing through the motor itself, not the one through the winding. Right? So E was calculated as 99.4. And the current there is 6 amps. So this gives 569.4 watts. And according to the conservation of energy, then this should be the same as the mechanical power. Because the only thing actually going through to create the mechanical power is what passes through the rotor itself, right? This is just generating the magnetic field. It has an effect on E, so it's accounted for in E. Any questions at this point? No.
I just have a quick clarification.
Yep.
So are we always assuming that the conservation of energy is taking?
Yeah. Okay, so the next one is the speed, torque, and efficiency we're going to skip. So speed and torque when the current here changes to 120 amps. So torque and speed for IA equals to 120 amps. So this is question C. How are we going to solve that? Any ideas? So we change the speed to 120. We change the voltage. We change the current to 120 amps. What changes in the circuit? Well, if the current flowing here changes, E will change. And then the power delivered to the motor will also change. So if you're interested in power, torque, and speed, we first need to recalculate E. What is the new E now? The new E is the same as is the same equation. V equals to RI plus E. E equals to 100 minus 0.1 times 120. Which gives 88 volts. 88 volts. Okay. So the back EMF here has changed. If the back EMF changes, what also changes? The speed of the motor changes, because we know that the relation between E and the speed is simply proportional. The greater the speed, the greater E. There's a proportionality constant there. So how do we find now the new speed? Well, we had the speed at this value here. The speed at this value was 1000 RPM. If now this value changes to 88, then the speed will also change proportionally to that. Right, so when the current goes to 120 amps, the EMF changes to 88, and because we know that there is the relation between the speed and the back EMF is constant, we can simply use that linear assumption to recalculate the new voltage, the new speed. So we know that at 99.4, we were at 1000 RPM. And now at 88 volts, we will be at a new speed. Now we know that speed and EMF are constant, and that's where we can take this relation from. We've solved for x that there we get 5.31 RPM, or 92.71 radians per second. Interesting. So the speed of the motor decreased and the current increased. So what happened there? What happened there? What would make this happen? What would make the speed drop so much and the current increase so much?
Torque.
A torque, exactly. A load has been applied to the motor drives a load, the speed now decreases, the speed decreases, so this E here also decreases, which means that from the balance of forces, there is less voltage being generated here against this current. The current increases and increases to supply the required torque that has been applied to the motor to lower the speed. How we calculate this torque now? How do you calculate the torque?
Can we use the same formula like as before, the half I squared DL d theta?
Half I squared.
Can't you just use power?
It's just the power, right? It would just be the power, because the power maintains. So we can still say that T times omega, torque times speed, equals to voltage times current. We have all these except the torque. So the torque would be the new E, 88, the new I, 120, the new speed in radians per second, 92.71. And this gives us the torque as 113.9 Newton meters. 113 Newton meters. All right, so this torque was applied. The motor is slowed down to run this torque, to deliver this torque. So to reach that, need to increase the current. Another way to see this is that as the motor is slowed down, the voltage generated here drops, which leaves more current flowing through this resistor. Okay, any questions? Yeah.
Why isn't the power in this case not the same as the power we had calculated before?
Because the operating condition has changed. Now there is an external power being applied to the motor to move this. The power we calculated before was probably at a no load, where it didn't have a load. Now there is a load acting on the motor, and that's why the power changes.
Okay, thank you.
Yeah. Okay, so let me see. There's one more thing that I wanted to calculate, provided that I find my notes. And that would be the stall torque. So today it's almost 10 already. That's probably the longest lecture ever for power electronics. But well, at least you have this recorded later for future reference. Is there any questions about this? Or I'm gonna move on to the last question, which is the stall torque. So I'll let you think about how to calculate the stall torque. In the meantime, how you guys would calculate the stall torque? What is the first thing we need to calculate the stall torque?
Is it V over R?
V over R, exactly. So in other words, I think what you want to say is the current at zero speed. Right, the current at zero speed, which is indeed V over R. Right, because at no speed, there is no back EMF, E is zero. If E is zero, the only thing opposing current through that inner loop there is that resistance. What else we need to calculate the torque? and no load. Sorry, the stall torque. What else we need? We need the torque constant. We need the torque constant. So the torque constant, luckily, is the same as the speed constant. And the speed constant we can calculate. That's through the back EMF. E equals K times phi times omega. And the torque is K times phi times I. So we need K times phi. We can isolate this from the first one. K times phi equals to omega over E. This constant doesn't change during operation, so we can take any operating point and calculate this constant. Let's take the first one at a no load. Omega was 99.4, and the voltage, the speed, this is reversed.
Oh, sir, isn't it E over?
Yeah. So we have this the opposite way here. We have E. So omega is 1,000 2 pi over 60 divided by 99.4. Can someone calculate this? This is supposed to give 0.94. Is that correct? Because I don't know if I reversed this now in my calculations. What is this value here?
I got 1.05.
1.05. Okay. Yeah, I just flipped the this in my calculations. Okay, so this is the constant that you can now use here. So the torque now becomes K times phi, which is here 1.05 times the current. What is the current? The current is the stall current. The stall current implies that this is not rotating. If this is not rotating, the only thing opposing current in this loop is this resistor. We can write the same expression again. We have V equals to IR plus E, which is 0, right? When omega is 0, which means that the current will simply be V over R, which happens to be 100 volts divided by 0.1 ohms, 1,000 amps. 1,000 amps. So this is 1,000 amps. And this gives then 1,050 Newton meters of stall torque, right? Of stall torque. So if you hold the motor steady and turn it on, it will develop this much torque. Of course, this torque is not the nominal torque, is much higher than the nominal torque. We notice here by the 1,000 amps is also something that's not trivial to deliver to a motor at 1,000 amps. The motor will probably burn down in a few milliseconds if this stall torque is sustained. But as the motor now starts to rotate, because there is a torque, so we're going to start to rotate, what happens? It starts to rotate, there is a back EMF here, which will oppose this current. And as it opposes the current drops. And of course, so does the torque. And then eventually it reaches a steady state at the nominal torque if let to run at no load condition. Okay. So thank you everybody who stayed until the end. If there are no more questions, I'll see you again on Thursday. I have office hours today, and I still have a few spots available. If anybody has any questions, just drop in. All right. Have a good day.